Yeah, as one of you were saying, the advantage of OFDM for the selection of LTE is that I said it provides an elegant solution to multipath interference. Then it has reduced computational complexity, right? Then the graceful degradation of performance under excess delay, right? It is possible to exploit frequency diversity. Then it enables efficient multi-access scheme like OFDM and other things. Then it is robust against narrowband interference. Then I said it is suitable for coherent demodulation. And this OFDM facilitates the use of MIMO technique, right? And it supports, right, the broadcast services efficiently. So these are some of the advantages of FDM, which has led to its selection for the LTE. Okay, and this OFDM is also one of the key enabling technology which is used in LTE design, right? And the second one, what I said is the SCFD, that is a single carrier frequency domain equalization, or and as well as SCFDMA, right? So like that, there are 5 key enabling technologies, right? The third one is channel dependent multi-user resource scheduling, and the fourth one is the multi-antenna techniques. So where we say the multi-antenna techniques supported in LTE includes transmit diversity, beam forming, spatial multiplexing, and as well as multi-user MIMO. Okay. Then the last one is it supports IP-based flat network architecture. So here flat means the number of components in the network has been reduced. So I think that the diagram I have shown from 2G to 4G, how the number of elements in the network has been reduced, right? So to say that in 4G, E node B is what we call a base station in 2G and other things. So in here we say it is E node B, which will be directly connected to SAE gateway, right? That is the data plane, and the control plane is connected to MME, that is mobility management entity. Then I have discussed about the network architecture, LTE and all. Fine, I think so. That is all about the model 1 first part, and second part I discussed about what path loss, shadowing, then statistical channel modeling, right? And as well as how do we mitigate narrowband fading and as well as broadband fading. Then we have come to the second module, which deals about the OFDM. Okay, so in the morning I said how the circular convolution of the input sequence with the channel impulse response made the OFDM symbol is ISI free, right? Inter-symbol interference free. So I said I will just give one example, so which will make you to understand clearly how output of the channel depends only on the present symbol, not on the previous symbols. Is that fine? Yes, I'm asking if I give one example, is that fine? No response. Everybody busy? No, if you are interested, I will tell this example. It is not for examination purpose, just for understanding I'm telling.
Yes, sir.
Want me to tell or not?
Yes, sir.
Yes, I want response. If you all feel that, yes, please give explanation about how this circular convolution means how the linear convolution has been converted into circular. With example, I can.
Yes, sir.
Yeah. Okay, so to begin with, just let me say how do I write the intersymbol interference channel? Okay, how do I express that the output of the channel is affected by intersymbol interference? Okay. So let me write the ISI. ISI means intersymbol interference. Okay. See, ISI channel, intersymbol interference channel, has been described as so I can describe the intersymbol interference channel as like this. See, if I say Y, I think, yeah. So if I write Y of M, right? Y of M is equal to H of 0, right? Then X of N, or I can say yeah, just I will write the same symbol, that is X of M plus H of 0 into X of M plus H of 1 into X of M minus 1, okay, plus I say this is a noise, okay, last term is a noise. So just let me say, so this is Y of M is what? This one is the received symbol, what I can say, received symbol at a time M. Received symbol at a time M. Okay. And this one X of M is the what? Transmitted symbol. This one is the transmitted symbol at a time M. At a time M, right? And this X of M minus 1 is the what? Is the transmitted symbol, is the transmitted symbol at a time M minus 1. At a time M minus 1. Okay. And I said this is noise. It may be additive noise and other. Okay. So which is not considered in our discussion. Additive noise always will be there. So this X of M, just say how I describe the intersymbol interference channel. I describe the intersymbol interference channel will be like this. So this is the received symbol at a time M, right? And this is the transmitted symbol at time M. And this X of M minus 1 is the transmitted symbol at a time M minus 1. Right? So what I can say, this X of M is the present symbol, right? X of M minus 1 is the what? Past symbol, right? Hope you are understanding what I am saying. X of M is the present symbol. Right here, is it fine? Is the present symbol, this X of M, okay? And this X of M minus 1 is the past symbol. Fine. So this is what we say, means the received symbol at a time depends on what? Present symbol and as well as the past symbols also. Okay, along with the noise. So this is how we say what is the output of the channel which is having intersymbol interference. Yes, hope this point is clear. And you all know what is h of 0, h of 1, and so on. These are the channel gains. Yes, is this clear what I am asking? Hello?
Yes,
Yes, I
sir.
am asking you people only. How do I represent or how do I describe the intersymbol interference channel? I wrote here, output of the channel will be is this y of m is equal to h of 0, x of m plus h of 1, x of m minus 1, and so on, right? Plus the noise. I said y of m is the what? Is the received symbol at time m, and x of m is the what? Is the transmitted symbol at time m, and x of m minus 1 is the transmitted symbol at time m minus 1. I say this x of m is a present symbol and x of m minus 1 is the past symbol, right? So present, past, both are depending here. So that is why I say there is an intersymbol interference in this. So how this OFDM means the use of intersymbol interference, that the use of orthogonal frequency division multiplexing can overcome this intersymbol interference, right? So within that symbol. So that is what we need to understand, right? Yes, hope you're all there with me. What I'm saying, are you understanding? No response only.
Yes, sir.
Okay. No, if you are there, then if you're interacting, if you're able to understand, because these things will not be put so clearly in text, means as part of your syllabus. Just to make you understand, I'm taking this extra. Fine. Okay, now let me say how the OFDM overcomes this intersymbol interference, right? With low complexity. Okay. So to understand that, let me explain. Sir. Let me consider I wanted to transmit, okay, some 4 symbols. Just for understanding, I'm writing this one. So let me write x of 0, okay, I think x of 0, comma, x of 1, then x of 2, then x of 3. Okay, so I wanted to transmit these 4 symbols, okay, with 4 subcarriers. Yeah, so let me say here the value of n is 4, I can say. That is 4 symbols. 4 symbols. And the number of subcarriers, okay. Number of subcarriers, also I'm denoting with the same letter, is also 4. So I can use 4 subcarriers. Okay. So what I wanted to say here is these n symbols will be loaded onto the n subcarriers. So these n symbols will be loaded onto the L subcarriers. I can so instead of making you this one, let me use a different alphabet. So let me say L, where L is the subcarrier. Okay. So n symbols are loaded onto the L subcarriers, so which I denote as x of L. Okay. So as I said, no, x of 0, x of 1, x of 2, and x of 3. These are the 4 symbols what I wanted to transmit, right? So these are the 4 symbols what I wanted to transmit. Symbols to be transmitted. I am loading each symbol onto each subcarrier. So I can say what is the IDFT of these symbols. If I miss here 4 symbols are there, so the value of n. So usually it's a 4-point DFT, you can say, right? So I have to use n-point IDFT, right? That is inverse discrete Fourier transform. Since here the value of n can be 4, so if I take the IDFT of these 4 symbols, I can write what? So let me write this by taking IDFT. So I can write x of 0, right? Then x of 1, then x of 2, then x of 3, right? So these are the IDFT samples. Is this fine? These are the inverse discrete Fourier transform samples. Okay. And as I said, y of m. Sorry. So in time domain, I wrote y of n will be equal to what I said, x of n, right? Circular convolution with h of n. Right, in frequency domain, I wrote y of m will be equal to h of m into x of m. Right, so with this I said the circular convolution, right, makes what it will convert. The circular convolution in frequency domain will be what? Product of, means it becomes a product of their Fourier transform, right? So the circular convolution, just I will write this circular convolution, this circular convolution becomes what? Becomes product in frequency domain, right? Product in frequency domain. Fine. So means this linear convolution has been converted into circular convolution by adding a cyclic prefix, I said, right? By adding the specific redundancy, which is known as cyclic prefix, to the transmitted vector, I will be able to convert that linear convolution into a circular convolution, I said. So let us again consider this is my sequence, I said, no? So for these samples, I will be adding the prefix, right? So what is that prefix I can write? So if I say x of 0, then x of 1, x of 2, x of 3, right? So I can take the last symbol, x of 3, and I can write it here. So I am prefixing the last symbol. Okay, so this one, I call it as the cyclic prefix. So this one here, we say prefix, no? Right? I'm adding at the beginning. I'm taking some portion of the symbols, I'm prefixing it. So this is known as the cyclic prefix. Cyclic prefix. So the length of the cyclic prefix and all we'll see later on. So now, right now, I'm taking one symbol or one data bit, what I can say. Here I'm talking about symbol, right? One symbol, and I'm prefixing it here at the beginning, right? So with this, so x of 3 I made at the beginning. Then after adding this prefix, right? After adding this prefix, what I can say, let me write as what, x of 3, right? Then just you can put comma here just to understand it is all right. So x of 3, then x of 0, then x of 1, then x of 2, right? Then x of 3. So this will be my block, okay, after adding cyclic prefix. And this will be, okay, so this is the block, OFDM symbol block, what I am saying now. This is my block, OFDM symbol block I can write, okay, OFDM symbol block after adding cyclic prefix. Just I write CP, okay, CP means cyclic prefix. Is that fine? And this is the thing which is transmitted over the channel, okay. So this one only is going to be transmitted over the channel. This thing is going to be transmitted over channel. Fine. So now let me write the output of the channel. So output of the channel as what I wrote at the ISI model. With respect to ISI model, if I want to write, so I said y of m, na, right? So y of m will be equal to, I wrote how do I model the ASI channel, right? So let me write here h of 0 into, I repeat once again, x of m plus h of 1 x of m minus 1 plus, I say v of m is the noise, okay? So right now I am not bothering about this. Let me concentrate only on the symbols, the required data symbols. So noise I am assuming it is 0, okay? So what I can write for when m is 0, yes, any one of you can say what I can write for m is 0, y of 0 will be equal to what I can write. Yes, with the above equation, I am asking when m equal to 0, what is the expression I can write for y of 0? Yes, students should respond. I need not again switch over the domain and ask the people name. Yes, Navya, you're saying something?
H of 0 into x of 0.
H of 0 into x of
0
plus h of 1
x
into x
minus
of, yeah, it will be x of minus 1, right? Similarly, I will stop with this, right? So I said I will not consider this one. I will assume it is 0, right? Okay. Similarly, I can write, I mean, so here the value of m is 4, right? So I keep extending, right? So what value I can substitute for x of minus 1? See, x of minus 1 I got now here. So in this, with respect to this, whatever I written, transmitted symbol over the channel. Here, what is x of minus 1?
x of 3.
Yeah. See, this is my x of minus 1, right? Because this is x of 0. So I can replace x of minus 1 by x of 3. Okay, so I can write h of 0 into x of 0 plus h of 1 into x of 3. Yes, is this fine? Yeah, similarly, sorry. Yeah, when m is 1. So when m is 1, yes, any other student can say what I can write? Yes, any other student, when m is 1. Yes, quickly. See, now has responded. Similar to that, what about Vidhu? Vidhu, can you say what can I write for m is equal to 1? Vidhu is there. Oh. Yes, Sonali, can you say? Sonali. Yes,
So
Sonali.
h of 0
Yeah,
x
Vidhu, tell
of
me.
1.
Yeah. What means h of 0?
X of 1
Yeah, x of 1.
plus h of 1
Yeah,
and x of 0.
x of 0, right? X of
Yes.
0. Very good, man. So this is the value I get when m equal to 1. So in the same way, I can write for two more values. I think I expect next Sonali to say. Yes, Sonali, can you say what can I write for m is equal to 2? That is y of 2.
Yes, sir. H of 0,
Yeah, h of 0.
x of 2
Yeah, x of 2.
plus h of 1
Yeah, plus h of 1.
and x of 1.
X of 1, right?
Yes, sir.
Yeah, thank you. So similarly, for m equal to 3, some other student without naming by me voluntarily can say no. Yes, y of 3. Yes, be fast. Somebody. I think you want me to name it. Yes, Chaitra, can you say? Chaitra is here. Chaitra. No. Yes, what about Ashwin? Ashwin. Hello. No, Ashwin. What about Ritu?
Sir, h of 0 into h of
1 minute. Okay, you're saying h of 0.
into h of x of 3
Yeah, x of 3.
plus
Uh,
h of 1
yeah, h of 1
into x of 2.
into x of 2, right? Yeah. So we have obtained these equations. That is when when m is 0, this is y of 0. Then when m is 1, this is y of 1. Then y of 2 and y of 3, right? So just let me say how the circular convolution is happening here. I think okay with here. So hope you people have noted these things. I think I expect you people to say, okay, what value I can write. So these are all y of 0, y of 1 and y of 2, y of 3. These are all what? These are all the received symbols, right? So these are all the received symbols. Okay. So looking at this expression, I don't know how many of you are able to say that yes, there is a circular convolution in this expression. I think to give a better clarity, just let me write here only. So, okay, so let me first draw just one line. Okay, so let me represent these input sequences now, x of 0, then x of 1, okay, then x of 2, then x of 3 with some magnitude. Okay, I will represent, I'm representing these input sequences with some magnitude. Okay. Is that fine? So now, so when m is 0, okay. So when m is 0, that is y of 0, right? So what we got? This one, right? That is h of 0 into x of 0. So h of 0 into x of 0. So let me draw some line here. Yeah. So if I take this as m equal to 0 line, okay. So here, what can I write? Just for understanding, see, x of 0 is there, right? X of 0 and h of 0 is there. X of 0 and h of 0. So let me write here h of 0. This point, h of 0. because x of 0 is there, right? Yeah. Then what is there? X of 3 is there, right? So x of 1 and x of 2 are missing here. Hope you're understanding what I'm saying with respect to y of 0. So h of 0 is there with x of 0, but with x of 1 and x of 2 are not there, right? So I can write here 0. Hope you're getting what I'm saying. Then x of 3 is multiplied by h of 1. So here h of 1 is multiplied. Yes, hope got this point. Why I wrote here h of 0, then 0, then 0, then h of 1. Just I represented in this manner. Okay, for y of 0, that is when m equal to 0, right? In the same way, I can write for other things also. That is, if I take it here, another line, let me say. So in the same way, is it possible to say, any one of you? So what I can write with respect to y of 1 expression, y of 1. So this is for y of 0, right? M equal to 0 means y of 0. So y of 1 is what? H of 0, x of 1 is there. Means at x of 1, this is x of 1, right? Here I get h of 0, right? Hope you're understanding what I'm saying. Then at x of 0, what I have? Yes, I don't know how many of you are able to get this point. See, this is the point, right? Y of 1. So this is when m equal to 1, right? So at x of 0, at x of 0, I have h of 1. So let me write this h of 1 here, right? Then next one is what? At x of 1, I have h of 0. So I wrote that one. Then at x of 2 and x of 3, no points, right? So I can write 0, 0. Right? So I hope by this time you might have got the idea how there is a circular shift. Then from when m equal to 0 to m equal to 1, see this h of 1, no? This h of 1 has been moved here, right? Last one has been moved here. Okay. Similarly, we can draw for other things also. That is for what I can say. This is when m equal to 2. And similarly, you can draw for when m equal to 3 also. So is it possible to quickly say from your end? Other students who can say for m equal to 2, that is y of 2. See, y of 2, for h of 0, it is 0 only, right? For x of 0, I need to mark 4 points, right? 4 points. See, y of 2 is what? Y of 2. Here only it is there, right? H of 0, x of 2. Then another h of 1, x of 1. Means at x of 1, I have h of 1. Means this is h of x of 1, no? So here I have h of 1. Then at x of 2, I have h of 0. So at this point, I have h of 0. And here it will be 0. And this is also is 0. Hope this point is clear. And then when m equal to 3. So when m equal to 3, I have these 2 points. That is x of 2 and x of 3. So x of 2 and see if I mark 4 points here. Okay. So x of 0 and x of 1 both are 0, right? X of 1 and x of 2 is 0. X of 0 and x of 1 is 0. Then I have for x of 2 and x of 3. So x of 2 I have h of 1. For x of 2 I have h of 1. For x of 3 I have h of 0. Right? So looking at this, I think I would have written one over the other because of I have equations here. So that is why I shifted here, right? So are you able to see this shift? See this h of 1 has been shifted to first, right? Then again it is moved further. Right? For the next this one, see h of 1 has been moved here. Yes? Are you getting my point? H of 1 has been moved. Then next one is again it is moved here, right? So it means this 0 has come here, right? This 0 has come here. Then what happened? Yes, then what happened? This 0 has come here, right? And this 0 has been shifted. So it is in circular fashion, what I wanted to say, right? So this is how there will be a circular shift of the channel taps, what I can say. So this is H of 0, H of 1, H of 2 and all what? They are the channel taps we can say. Okay. So because of that, we write the output of the channel is the circular convolution. Hope you're getting what I'm saying. Why we don't write as a linear convolution, why we wrote as a circular convolution. This is what is the reason, right? So that is why I wrote y of m, okay, y of m, or I can say in time domain n also you can take y of n, right? Y of n will be equal to x of n circular convolved with h of n. Hope you got my point. Why do we say it is circular convolution? So this is in time domain, we say circular convolution. In frequency domain, already I wrote it is the multiplication of their Fourier transform. Okay. Yes, I don't know whether I could convey the concept or not. If I'm not getting any response also. Yes, my dear students, please respond. If you want to continue, I will continue. Otherwise, I will leave. Have you understood what I said? How there will be a circular shift happens, and how I say when I pass the input sequence to the channel, though it is by nature it has to be linear, but by adding cyclic prefix, I will be able to get that circular shift. That's what I wanted to convey.
Yes, sir.
Yes. Yeah. Okay. At least responding. Fine. Good. So the last point, what I wanted to say, what I was telling in the morning, is that. So this is what in time domain I said, na. Then I wrote in frequency domain. In frequency domain, I said y of m will be equal to h of m into x of m, right? So plus the additive noise and other term will be there. I said I'm leaving that additive noise. So I said when m equal to 0 means the present symbol, right? So it depends only on the present input sequence, not on any other this one, right? So I can write when m is 0, right? When m is 0, like what I can write, it will be h of 0 into x of 0. So x of 0 is a what? Present symbol, what I said, right? So it depends, means output sequence depends only on the present sequence. Similarly, you can write for other values of m. That is y of 1 will be equal to what I can write, h of 1 into x of 1, right? Then y of 2 is equal to h of 2 into x of 2. Similarly, y of 3 will be equal to h of 3 into x of 3. Okay, so this is what? This is the current output, what I can say. This one, called y of 0, y of 1, y of 2, y of 3 is the what? This is the current output. Okay, current output. And here, this x of 1, x of 0, that is x of 0, x of 1, x of 2, and x of 3 are the what? Current symbol, current input symbol, right? So current symbol. And I can say current input symbol. Okay, the current output symbol present only on the current input symbol. So with that, we say it is free from inter-symbol interference. Okay. Yes, understood this point, how we have eliminated or mitigated, how we have eliminated inter-symbol interference, that is ISI, right, in frequency domain. in frequency domain of each OFDM symbol. Of each OFDM symbol. Yes, I think you should be able to give this as an example. Okay, first you need to go with the ISI channel model, then consider some 4 symbols, right? Take the IDFT of that. Then you, I said to add the cyclic prefix, means I have taken last symbol, I prefixed that, right? After prefixing that, then that block will be transmitted over the channel. So after transmitting that block over the channel, means which is added by cyclic prefix, I wrote what is the output of the channel, right? Then I conveyed with the diagram how the channel taps are in the circular fashion. So with that, how do I say output depends only on the present input, not on the past input. Okay, so this is how we can defend or convince that how the ISI is eliminated in the OFDM symbol. Yes, so is this fine? So I repeat once again, by employing cyclic prefix, okay, the intersymbol interference, okay, has been removed in the frequency domain. So I think I will write that point also. By employing cyclic prefix. By employing cyclic prefix. So by employing cyclic prefix. So if you remember my initial is what, CP, right? So by cyclic prefix, which say in short CP, we are able to eliminate the intersymbol interference in the OFDM symbol, in each of the OFDM symbol. Okay, so I think let me stop with this for today's